Project, predict the electrical energy output of a combined cycle power plant, which uses a combination of gas turbines, steam turbines, and heat recovery steam generators to generate power. We have a set of 9,568 hourly average ambient environmental readings from sensors at the power plant which we will use in our model. The columns in the data consist of hourly average ambient variables, temperature, T, in the range 1.81 degrees Celsius to 37.11 degrees Celsius, ambient pressure, AP, in the range 992.89 to 1033.30 millibar, relative humidity, RH, in the range 25.56% to 100.16%, exhaust vacuum, V, in the range 25.36 to 81.56 centimeters Hg, net hourly electrical energy output, P, 420.26 to 495.76 megawatts, target we are trying to predict. Machine learning approach. The problem of predicting the electrical energy output of a combined cycle power plant can be addressed using a regression machine learning approach. Regression is suitable because we are trying to predict a continuous output variable, net hourly electrical energy output, based on multiple input variables, hourly average ambient variables, output metric, an appropriate output metric to evaluate the performance of the model in predicting the electrical energy output could be mean absolute error, MAE. MAE measures the average absolute difference between the predicted and actual values, providing a measure of how well the model is performing in terms of the magnitude of errors. Possible features. The possible features to be used in the model are the hourly average ambient variables, temperature, T, ambient pressure, AP, relative humidity, RH, and exhaust vacuum, V. Different algorithms. We can consider multiple regression algorithms for building the model, such as linear regression, decision tree regression, random forest regression, support vector regression, and neural network regression. Validation strategy. For comparing different models, we can use k-fold cross-validation. This involves splitting the training data into k subsets, folds, training the model on k1 folds, and validating it on the remaining fold. This process is repeated k times, with each fold being used as a validation set once. This approach provides a more robust estimate of model performance than a fixed validation set. Model comparison and selection. We will compare at least two different models using cross-validation and evaluate their performance using the MAE metric. The models may include different algorithms or variations in features and hyperparameters. The model with the lowest MAE on the validation set will be selected as the final model. Here linear regression and random forest regression are compared. Value for linear model MAE is 3.59 whereas value for random forest model MAE, 2.32. Evaluation of final model. The final model's performance will be evaluated using the same MAE metric on the test set, which was not used during model selection. This will provide an unbiased estimate of how well the model is likely to perform on unseen data.